Hello YouTube and welcome. In this video, we are going to write a UEL code for a plane stress structure subjected to concentrated and distributed loads using triangular elements. So we note that the shape functions of a triangular element are according to this image. Assuming a 3-node element with 3 integration points, the shape functions and their derivatives are like this. The integration process, such as the location of the integration points and their weights, is according to this image. For more information about the coding process, take a look at my other video in which I explain the whole process step by step. First, let's take a look at the model. The model includes a 1x1 plane stress structure made of steel with 200 gigapascals for Young's modulus and 0.3 for the Poisson's ratio. We are going to do a static step with nonlinear geometry set to off. The boundary conditions are according to this. First, we are going to close one edge with U1, U2 set to 0 and 2 point loads at the edge with the amount of 100 kilonewtons. The meshing consists of 32 triangular elements with linear geometric order CPS3. So now let's prepare the Imp file. So we have 25 nodes and 32 elements that we have to prepare. So the coordinates of the 25 nodes are here and our 32 elements are here. So our user element has 3 nodes and 2 properties, U1, U2 at each node, 2 coordinates, X, Y. And since I'm targeting only the stress components, I have only 12 variables. If you want to calculate other variables such as the velocity or acceleration, etc., you should add to these variables. Next, I am going to use a decoy element with almost 0 stiffness for visualization purposes. You can take a look at my other video in which I explained the whole thing and why we use a decoy element. Since Abacus does not know what element are you coding for visualization, you should use a decoy element. So if you look at our boundary conditions, nodes 5, 10, 15, 20, 25 are going to be closed, and the load is going to be applied at node 1 and node 21. So my support nodes are going to be nset named sub 5, 10, 15, 20, 25. Also, you can use the generate command. In this case, it is not going to be any difference. And I'm going to write a node set named push nodes 1 and 21. And my loadings is going to be concentrated load for the case push at node 1, node 21 in the directions of U1, U2, and the amount of load will be 100 kilonewtons. And here I'm going to write it in Newton. And my boundary condition is going to be my sub node set in which degrees of freedom in U1 and U2 direction will be closed. I only ask for SDVs in my decoy element to visualize the stress components. Abaqus automatically gives me the displacement vector U for each node, since it is going to be a variable in the solution, and I'm going to ask for the concentrated force to see where the forces are applied. So this concludes our Imp file. Continuing with the subroutine, we use a module named kvisual to transfer the results from UEL, here stress components, to UMath subroutine for visualization. In this example, we have 32 elements. Each has 3 nodes, and each node, or should I say the integration point, has 4 stress components. The process is explained in my other video. We know that in a linear static analysis, Abaqus asks for stiffness matrix, here denoted by A matrix, and the contribution of the element to the total force vector, indicated by right hand side RHS matrix. So we have 2 degrees of freedom in each node and 2 dimension x, y, 3 integration points, 32 number of elements, 4 number of SDVs, and we have 4 stress components, intense equal 4. First, we construct some zero matrices, and then the elasticity tensor. Next, do a loop over the integration points, which will have 3 loops. Get the shape functions and their derivatives, calculate the elements Jacobian, and use it to construct the B matrix. Moreover, we call the SDVs, which are stress components from the previous increment, and put them in a local vector. Calculate the strain increment and then calculate the elemental stresses. And then the force vector, as you can see it in the highlighted area. Next, we update the right hand side matrix. We do the same here. We calculate the stiffness matrix of the element. Then we store the calculated stresses into the state V's, and we use them for the next increment. Finally, we pass the results using the seek out matrix. Remember that in the integration process shown here, we have to divide the sigmas by 2. So we do that outside of the loop for the stiffness matrix and the right hand side matrix. Also, the shape functions are here in an external subroutine, as you can see it here, which are in accord with the slides I have shown. So this concludes our UEL subroutine. For more information, you can take a look at my other videos in this field. Now we are going to compare the results from Abaqus and our subroutine. Now we are going to compare the results from our subroutine and the results from Abaqus. I've already submitted the job, and I'm going to only show you the results. The window on the left shows the results from Abaqus Solver, and the window on the right is from the UEL subroutine. First, we are going to compare the displacement vector for component 2, U2 is the same here, and for example the SCV4, which is the shear component of the stress, you can see it, they are completely identical. Now we are going to use the subroutine to simulate a plane stress structure subjected to a distributed load on an edge. In the following example, we are going to use a distributed load instead of point loads. As you can see it here, the distributed load is a shear load with the amount of an odd number here, since I don't want to have any chance of being lucky for the distribution. So if you guys have paid attention, I did not construct a force vector for external loads in the previous example, since Abaqus automatically transfers the point loads to the global force. Now we are going to exploit that option. First, let's take a look at some fundamentals. Assume that we have an edge with a distributed load on it. We can assume a nodal reaction for this situation and divide them into this. Now we can use the finite element method to obtain nodal reactions and put them together. For example, if we have two elements that have the following distributed load, the nodal reaction force will be according to this. This vector here is identical to the equivalent node force vector. So for this purpose, I've written a MATLAB function that gives us the equivalent nodal force vector. In this code, we have to input the length of the surface, the number of nodes, thickness, and the amount of load. And when you run the code, it gives us the equivalent nodal force vector. Then we proceed as before and act like we have several point loads instead of a distributed load. Pay attention that the nodes inside the edge have identical loads, whereas the points at the edges have different loads, as you can see it here. So we have to be careful for this. Now we are going to use that point loads instead of this distributed load here. We are going to use a nodal set 6, 11, and 16 for our inside nodes, and a nodal set for nodes 1 and 21 for the different loads. As you can see it here, I have the concentrated load option with two node sets inside and edges in the direction 2 with the amount of minus 480 and minus 240 as according to this force vector. For more information about this coding procedure, you can take a look at my newly published book. Now I'm going to compare the results for this distributed load. So if you want to take a look at the displacement vector in the second direction, you can see that the results are identical. And for example, for the shear component of stress, you can see that they are identical. This concludes our video. If you find this video useful, please support me by subscribing and liking my videos. Thank you.